thanks everyone for joining here. You're plenty. That's nice. I like it. So I'm Claudio. I work for Airline Solutions. I'm a consultant, and I do Elixir on a daily basis, 3-4 days a week. The other day I have to do business development stuff and a lot of emailing, which is always enjoyable. So before we dig in the topic, just one quick thing. For people who are not in Tim Mecklen's talk about the nervous-based pancreatic replacement, when the videos are available, please go and watch it. It's been one of my favorite talks in recent years, and it's really full of good content and good ideas. That said, let's go to the topic for today. So we're going to talk about state today. We're going to talk about state from different perspectives, and we're going to talk about state hopefully from more than one angle that can be useful on a daily basis for any sort of application development you do, whether it's you're anywhere in the spectrum from embedded devices to web applications to event processing to the three things together. Just a quick mention, state, when we talk about state, we talk about any type of data that influences the behavior of the code you're writing, meaning anything that cannot be, basically can alter functionality of your code without altering what you pass to a function. This is a very convoluted way to describe it, so please forget about it. It just means anything is stashed in a database or in memory or anything like that. So state itself has a few properties. Like first one is it's useful. It's incredibly useful. In fact, without state, we would probably all just basically compute in Fibonacci. That's what we could do without state. It's difficult to model. Most of the times, we have the subtly complicated task of taking a chaotic mass of things and facts about reality, smash them into a data model that sort of makes sense for the knowledge we had at that point in time, and just hope for the best that it's still going to be good in 6 months. And I mean, spoiler alert, it basically never is. So it's difficult because maintaining it becomes difficult. You make a choice, you evaluate the trade-offs, but in the end, you are forced to hope and design for making changes over time that are supposed to be easy, and that's not always the case. So it's always important to spend a little bit of extra time when we design data models and when we decide to store things, because it will bite us back in the future if we don't think about it properly. The other thing about state is that it's precious, but it can be lost. And when it's lost, first of all, so it gets lost in ways that you couldn't predict or you didn't think about, or in a way that is so nasty that it takes you 3 days to figure out what exactly happened. And the other thing is that in that time, well, people want to use the thing you're building, so you, as best as you can, you need to recover it. And one of the main points about this talk is that there's a lot of conversation about fault tolerance and availability in terms of, hey, here's my set of processes, here's how they can fail and respawn, but I think we don't talk enough about the consequences of that in terms of how expensive it is to recreate a certain state that we had before the crash. So sometimes you get an application that starts performing badly, things crash, respawn, and at that point, you have to recreate that state. And the next 2 hours of your application are slow performance because you're just bottlenecking on the data you lost. And when I say you, it's me, by the way. Like this happens. So it's an hypothetical you with a mirror. So in other words, we always have to think about this. Or like the common thread about all of this is that every time we put in an extra table, it's a decision that has a lot of weight. More often than not, it becomes more important than the design pattern we choose or the other things that are much easier to refactor and change. Now, this is quite I mean, if you say state, you kind of have to mention this paper. But the reason why I mention this paper is, first of all, it's one of the few papers that I read in my life. I'm trying to read more papers, but it's an art. Like, you kind of have to get into them. So this paper from 2016, Out of the Tar Pit, the main point of the paper, and by the way, we're not going to talk about the paper itself for the rest of the talk, but it's just to mention, it's a research that shows that the majority of the bugs and the accidental complexity in pretty much any code base can be tied to state. So it's an interesting read. It's very approachable, and it gives you a good frame of reference around what we're going to talk about today. So you can keep it as a sort of a background to have behind. So when or this is just like a personal preference that ends up being reflected in talks. I like to talk about things with examples. So what we're going to do from now on, we're going to take a use case of a hypothetical thing that we want to build, and we're going to use that, and we're going to go through different iterations of how we could build it, trying to highlight the pros and cons and the trade-offs we make along the way. The application is, you can call it gigs near me, or if you want to spend more time on it and find a better name, please feel free to do it. But in general, it just means, given my location, in terms of coordinates, give me a list of gigs, or musical events around me. For each one of them, I want to know who's going to play in those at those events. And for each band, I want to know what's their latest published release, because maybe I don't know them, but they are nearby, so I can just like see that and then play the album and see if I like it. So it's a very small, it seems like very self-contained use case, which if you end up swapping around some of the terms, you can probably try to find something closer to the domain you normally work in or that you're interested in with similar constraints. So I like music, so this was easy for me to imagine and prototype on. Now, the example we have is that if you ping this endpoint, for example, you're going to get back a list of events with extra information. Now, the data model for this is that given a location, you have many events associated with it, so concerts near this address, pretty much. Each one of these events may have one or more artists involved into it. Each artist has one release, the last one published. For short, we're just going to call it release. So you can see that this relationship is pretty much always from left to right. Our use case always goes from the left to the right. So as long as we can go from a location all the way to the last piece of information, we are happy. We don't do, for the time being, we don't go the other way around. We don't go from a release to an artist to events to a location. Now, how do we do this? In practical terms, a possible way to implement this with that data is already available is to leverage two APIs. One is an API provided by Songkick, if you're not familiar with it, it's a service that allows you to pretty much do more than what I just described as a use case. But they offer a public API that you can use, and MusicBrainz, which is a community-maintained service that basically catalogs all published music around the world. So you can think about it as a way, in the same way you think about ISBN codes for books. Given a MusicBrainz ID, you point to a unique artifact in the world of a published piece of music. Now, the two APIs are tied together because Songkick is, they're kind enough to put MusicBrainz IDs where appropriate in their results, in the API results. So you can tie the two things together through that. How do you do that? How do we tie things together? In general, a location has IDs for the events that are happening at that location. An event has some metadata and the embedded list of artists that are going to play at that event. An artist is defined by some basic data, a MusicBrainz ID that ties it to the release. So that way we can follow the train completely left to right, complete our data model. Now, this specific design comes with specific pain points. Due to the constraints that the API have, you wouldn't be able to build this completely, you could, but you wouldn't be able to build this very efficiently if you delayed the request to the underlying APIs at request time of your service. In other words, you cannot just do that at that point in time, because particularly because of the MusicBrainz API, because each artist requires a separate API call to fetch their last release. Now, to give you some hypothetical numbers to keep in mind, a query for a single location gives you 20, 25 events, 1 or 2 artists in the worst case scenario for each one of them. You basically get a batch of 50 API calls for releases per location you monitor. So it goes up pretty quickly. On top of that, both APIs are rate limited because you should rate limit your APIs, and they're doing that. The default rate limit is very low. By the way, if you do anything like this, really good thing to do, write an email, customer support, pick up the phone and ask them kindly to raise the limit for you. If you also can put some money on the table, that makes it much easier to do. But otherwise, just be very polite and maybe they will be okay with it. But suffice to say that there's no way out for us. We need to keep a copy of that data. Now, when I say, I'm going to say just cache that data in this instance, but we're not talking about like a cache store in itself. We're just talking about keeping a copy of it for our use that doesn't require us to continuously go to the API to answer a specific question that comes from an endpoint. Finally, because it's HTTP APIs we are talking about, we never know when they change. Now, if suddenly there's a new gig near the hotel, and the last time I queried the API was 3 hours ago, then I will never know about it until I perform the same API call again and I update my own data. So we do need to think about polling and refresh. So it's not complicated on the surface, but it comes with like nitty-gritty, fiddly details that really make you hate this job once you have to go through them. So it's the kind of thing that, as best as you can, if you have like good tools to do it, then you don't have to get so upset about it. Let's start with iteration 1. So how do we solve this problem in a simple as possible scenario? So simple as possible scenario means that we can start by saying, okay, I've got one location with 2 coordinates. I have one process for it. One process that gets spawned once per location, meaning if you ask about the same location twice, you're not going to get a new process that does the work again. We always get the same one, which means that we keep track of these processes through a registry. A registry, and in terms of Beam, for people who are not familiar with it, is a module, is a thing in your application that basically gives you the ability to take a term, which could be a tuple, a string, whatever you like, and map it directly to a process, so that as long as you know the name of the thing you're looking for, you can interact with the process that is behind it. And each process is responsible to fetch and refresh their own data and keep it in its own memory space, right? So process with a PID 1, 2, 3 monitors a location X and Y and holds the entirety of the data. And that means that when you start fetching and then you start to get the releases, over time the process will basically change its own state until it finishes fetching everything. After that, we'll see what happens. So the life cycle of that process, this is where you could, if you think about it in terms of OTP, in terms of a gen server process that does this, it could just like cast itself some messages to schedule the next piece of work to do. So when the process starts, it fetches the events. Fetching the events contains information about location and events and artists. So that's one thing taken out of the way. and then it starts fetching the releases. So given these 50 artists, one by one, fetch the releases for each one of them. After a while, we just do like some cleanup. So after a while, that basically no one has asked about this location anymore. Maybe 24 hours after the last time we asked the process to give us some data, to read the data that is in memory, we can just say like, process self-destruct. You're done, you're finished, no one cares about it anymore. So in essence, we have a really, really isolated design because each process is completely separated from the other one, right? Things go wrong in that process, you try to talk to the API, you fail, the network goes down, like whatever it is, that process is going to go down, the other ones are going to be fine. It also scales predictably in terms of memory, because once you have a rough idea of the average size of the responses you're dealing with, like events are a certain size, locations are a certain size, you can do a back of the envelope calculation of how many of these processes you can handle on a single node. That's quite a powerful thing, because it gives you the ability to predictably think about what kind of infrastructure you may need for this project. And the expiry is easy, because if the process dies and cleans up, that no one has to go around and then look for orphans, and no one has to clean the remains of stale data. The concern is that if you don't do it properly, a single process could end up escalating and taking down the entirety of the tree, particularly if you have extended outages in the underlying APIs. There are ways to mitigate this, but it's very common to see in day-to-day development situations where you interact with external services and then you end up in a reboot cycle that ends up taking down the entire node. So a little bit of like extra checks around that. The major problem is a different one, though. The major problem is that you get duplicated data, because each process keeps its own copy of the data, and then even if the VM tries to do some optimization around data that is somewhat like shared, it's just not the same thing. You're going to get a lot of waste out of this. Now, let's tackle that. So let's fix the waste first. So what we need to do is basically take that data, move it out of the process. Now, there's a lot of literature around, like classic examples that you read about are, hey, I've got this data, I'm going to put it in an agent, then the agent is not flexible enough, I'm going to put it in a Gen server, then you do some load testing, it becomes slow because it's a single process, then use ETS and it fixes all problems. Now, it's necessary to expand a bit on that. The pattern is very repeatable and reusable, but it does come with some caveats to think about. So ETS tables are tables that you have in memory that exist as long as their parent process who spawned them exists. They can be created by a process and used by another one, which means that what we can do is store part of the data inside the process. So the location and the location is still mapped inside the process. We know which events in terms of ID the process has access to, but move the expensive data in ETS tables that are shared. And we fix the duplication. But we do need to clean up the storage, because if processes start to crash, we got intermittent failures, so we get unexpected failure scenarios, there may be stale data remaining, and that could cause memory leaks. As long as you have the data but not the references to it, it doesn't harm. If a process crashes and you lose the ability to say, go from location A to this list of events, it's not bad, but you're going to run out of memory. So it is bad. The life cycle is very similar, slightly changed. We basically start store. So we fetch the events, you just shove them in ETS. Then you fetch the releases and put them in ETS and go on as before. So the migration path from the previous solution to this one is very gradual. Like, it doesn't require a lot of work. So it's something you can do nicely. And it gives you the add benefit around memory, because you're more efficient around that. You also get a performance boost. This is something that there are various benchmarks around this that you can even try on your own, as long as you can load test the public API that you are working with. This tends to be fairly noticeable when you move from a single process holding data to ETS holding that data. Now, it may be a difference that doesn't matter for the type of load that you are thinking about for your application. Like, it may just be that that process would be enough, but it's just a really good payoff for a very small refactor. And you got another benefit, which is actually, this could be probably the most important one. So if you can read this top to bottom, the bottom to the top, the slide is much better. If you don't create the table, if the process does not create the table, but if you let the application process, the top level supervisor in your app, you let that process create the tables, then the only thing that can delete them is a node crash. So in a scenario where suddenly both of the APIs go completely down, all of your processes that try to refresh data, they crash miserably, everything is on fire, you're still in a position where a lot of the data is still there. So maybe you get into a scenario of unavailability for a few minutes, but the moment things go back to track and this process manages to stay alive, as long as you write code in a way that basically checks if the data is already there before refetching it, you can definitely improve a lot the situation of recovery. So your recovery can be much, much smoother. Now, the problem with this is that we haven't really finished, and you could pack this specific, like the next step and this one together. I just kept them separate to show exactly one specific part of the problem, but we said a process holds the notion of the event IDs that are at their location. Now, if we lose that relationship, we leave orphans in ETS. And really, don't be like a bad person with orphans. Like this, you don't do that. So next iteration, we move locations as well to ETS. So pretty much everything goes into a different memory space. This is what we don't do it just because we have a good reason to do this. Like, we thought about it, and that seems like a sensible solution for the problem we are working with. Now, that means that now we got a design that separates two parts of our application. One is around fetching and refreshing data. That's the process business. The other part is storing the data. That's handled outside of the process lifecycle. And that means that by having this clear separation of responsibilities, we achieve a best case scenario for recovery. Like, all the processes die, all the processes come back up. As long as the node itself didn't go down, the data is still all there, and you shouldn't have an impact on the performance of the application. The lifecycle is very similar. You basically fetch the same thing, store the location, that's the only change, fetch releases, and terminate. Again, another gradual refactor step. So not particularly, like you can definitely do it nicely and see how that changes. We do have faster concurrent lookups for everything now. Before, when we said, give me data for location X and Y, we would need to ask the process about it. Now the process can, like, it's not affected by that. We don't have to ask it. We just ask the data directly. We ask the ETS table, which means that we don't go to an extra step. If we don't have any data in ETS about that specific location, that's where we spawn the process. So we can afford at this point to be slightly lazy about respawning processes for specific location. We survive all of the refresh crashes. But we introduce a worst case scenario now that is different from before. And the scenario is that we have, in case of crashes, we are going to have stale data. By definition, that's going to be stale data because it was there before the process who is supposed to fetch it has been respawned. So what does it mean having stale data? Now, this is quite a, like, in my personal opinion, it's quite an important thing to think about. because stale data may still be useful, but sometimes we don't model it explicitly. Like, let's say that there's a 2-hour-long outage on the 2 underlying APIs, and I've got data that is 3 hours old. As long as I serve that data to my customer, to the end user, to the consumer of the API endpoint, and I just tell them, like, this is what I have, bear in mind that it's 3 hours old. Like, that's the best I could do. On a best effort basis, that's what I can do now. They can decide on their side if that's enough, if that's okay. So you shift perspective completely. From a user point of view, as long as you don't lie about how new the data is, it may be an acceptable scenario compared to not having any data at all. And to do this, you need to model it to keep track of this. Like, so if you just store data without any timestamp, without any awareness of when it was fetched, without any awareness of where, at one point in the life cycle of a refresh for a single location you are, then you cannot do this. So the important thing about this is that there's a little bit of metadata that you can collect about things, even when you store them in memory, because a lot of these things come pretty much for, not for free, but if you store them in Postgres or if you use Ecto, a lot of these things are already taken care for you. But when you store them in memory, just like double checking that you have a little bit of metadata about these things may save you in the long run. It also means that we need to think about stripping as a thing in the system, like cleaning up old stuff. So if you expire data about the location after 24 hours, basically at 24 hours plus 1, you could be able to just decide, if I see any data in my tables that is older than the life cycle of my processes, that data doesn't need to exist anymore. Let's just clean it up. It's probably there because a process crashed in a way that couldn't allow the cleanup that you would have set up in the life cycle of the process. Now, we're still in a position where if lightning strikes down the node we're working on, we are still screwed, because we have talked about the single node now. Now, a distributed scenario for this is, it will be a talk on its own. It's not, like, talking about distributed data is quite a big topic. So what I want to do at this point is just try to reason about the problem and then understand why you could go from one option or the other. Now, if we think about the shape of the data we talked about so far, is that it's discrete pieces of data linked by references, right? Location has event IDs, an artist has a music brains ID, and then you connect pieces together. That means that at any point in time, if I take a location, I can do my calculation and see, do I have everything in my in-memory data to consider this location complete? Like, do I have all of the data? If not, I can safely say, this is a partial piece of data. May still be useful, but it's partial. So we are able to do that. Now, when that happens, we can decide what to act on. We can just say, okay, let's requeue a refresh. Let's just like try to refill that data as best as we can, trying to fill the blanks that for some reason they got lost. And again, as long as we don't lie to the consumer or the client API for this data, that's going to be fine. It's the user may have the right expectations. Now, this could be a good candidate for sharding, this type of data shape, because if, like, sharding means you get the entirety of the data, and then you split it on different nodes, and then when you query a single node about it, you get the entirety of the data, including things that are on the other nodes, transparently. An example implementation of this that we could use to replace ETS, it's a library called shards, but really the library doesn't really matter. It's just conceptually, we are in a model where, because our data is already designed to account for partial data loss, then we could go for sharding. Worst case scenario, we lose a node, we lose the data that we need to refetch. Even in the case of a location, even in the case of a location that would be our primary piece of data, that without that we cannot do anything, we would be able to just say, look, I can't find the location, but there's a process for it. So it must be a bit of a weird situation. So let me just force a refresh on that process. So building this on a case-by-case basis, we can fill all of the, like, little bit fiddly, but we can fill all of these blanks and try to somewhat like try to fill the blanks that we left around. The other option is just use Postgres, right? You can still go back there. Like, and this is like to me, that's the interesting bit. That's where we start from normally. Like, we always start from or at least it's a common way. We start from an application, we put a database underneath, and we try as best as we can to contain the state in there, and then so that we can scale horizontally, and then everything is on the surface more available because we got more nodes. It actually is not, because we have a single point of failure underneath. But it is a possible solution to the problem we just described. It has different trade-offs compared to other possible solutions. And if you look at it as one of the possible alternatives at the point of deciding what do I want to do to guarantee that my data survives the existence of this node, then it's slightly change your perspective. Because it just doesn't mean like putting it there from the start because it's always there. That may not be the best solution, or that may not be the trade-off that you want to do at this point. The other problem which we hinted about, but it's actually a major, it actually has a very strong impact, is rate limiting. Meaning that rate limiting, we need to think about it seriously. We cannot interact with APIs just by calling external APIs whenever you like, because there's a rate limit. So you can stick a queue in front of it. So I had to fetch 50 releases. I will put them in a queue and then go as fast as I'm allowed without basically going over the rate limit. And the other thing is that if you're working with a service that has a rate limit, it's always a good idea to have an implementation in your application of the same rate limit. So that way you can avoid hitting the real one and then having to spend half an hour on the phone or sending emails, and then particularly, this is more of a, I guess, a problem when you work from Europe. That always happens when the time zone doesn't help, because people are already gone home at the end of the day, and then you have to wait the day after. So because you got a rate limit, also load testing is important. It's even more important than normally, because load testing with a rate limit scenario means that you have to worry about not only about the consequences of queuing a lot of stuff in your app and filling up basically memory, but also it forces you to understand what this implies from a user point of view. Can you afford to have an API endpoint that gives you just a little information very slowly? Is that acceptable? If it is, you're good. So summary. Focus on status. So think about all of our endpoint has a status, and each resource may declare its own status, if it's being fetched, or if it's still, or if it's done and can be consumed. Having explicitness around this forces the consumers of the API to handle the corner cases as much as they can. Or if they decide to ignore them, at least they decide to ignore, they have to take that decision. But you do have a sort of like a better typing on top of the resources you fetch when you are in a scenario where you cannot just get everything at the same time. The other thing is that it's always a good rule of thumb assuming the data will eventually be inconsistent. It will also be eventually consistent, but in our case, inconsistent is the problem. It can be lost in different ways in different places. If you try to tackle that problem up front and prevent this from happening, that's going to be difficult. It's better to focus on the recovery. So all of the extra things that we needed to do that we talked about, they were all focused on, given that I'm going to be swimming in a sea of pain. Where did that come from? You write code to recover from that. Sorry, it was really bad. Distribution, that's powerful, that's good, but then you may increase the inconsistency scenario. So there are definitely good scenarios to reach out for that, even for data that is not just transient data, but they come with specific trade-offs which need to be explored before making the plunge. And the other thing is that there's a wide arsenal of tools that we can use, like queues and rate limiters, backoffs with APIs. There are actually 3 examples, not 2. These things need to be planned. OTP comes with a really good baseline in terms of restarting and recovering things, but it doesn't come with these things built in. And sometimes people get surprised because, for example, backoff is not built in. Backoff is a decision that you take when you need to. Like it's a tool that you put in. These tools, they are tools that, if you come from different languages than Elixir, they're already there. And if you used them before, please feel free to use them again, because they are still useful. You just have to put them in a slightly different life cycle, but all of these things are still useful. And thank you. Any questions? That's me.
The room is a little bit big, so if you can come a little bit closer, if you are far away for the questions, will be great for us. Questions?
Okay, while that happens, before I forget, we're hiring. So if you're interested, I'm allowed because we're sponsoring, right? I can say this. We're hiring for Elixir around the world. Elixir, there's RabbitMQ as well, which we do support, and React as well. There's a bunch of stuff we're doing. Feel free to come to me and talk if needed.
It's a great company.
Thank you. Appreciate it.
Yeah, it is. So, questions? Anyone? Don't be shy. Okay. 1, 2, 3. Okay.
All right,
okay.
cool.
Thank you.